Good morning or good afternoon, wherever you are, and welcome to this presentation from the National Precast Concrete Association on fiber reinforced concrete, new ACI design guides, and other developments. My name is Michael Mahoney. I am a professionally licensed engineer, originally out of Canada, currently the Director of Marketing and Technology for fiber reinforced concrete. I've been working with fibers in concrete from a academic, laboratory environment up into working with contractors and producers, and about 25 years experience now, and looking forward to talking to you today about how fiber reinforced concrete has evolved, especially over the past decade, and is becoming much more common in everyday construction. There's a new document from ACI, 544.4R, that was published in 2018 that is now being used extensively by many engineers around the world in terms of helping them produce, work with, and create applications for fiber reinforced concrete. Those applications go all through flooring, precast, shotcrete, paving, but for today, we're going to spend a little bit of discussion talking about how fibers can be useful in precast concrete applications. Before we do that, though, I always like to start these presentations with just a little bit of outside the box. A lot of these webinars, and I'm sure many of you have been on these over the last year, kind of dive right into the subject matter, and sometimes we don't take a look a little bit farther back. I'm a concrete engineer by background, by training, and I like to pick up some of the fun facts, and I'd like to share some of those with you here before we kind of dive into the technical part of this presentation. But you know, concrete's all around us, and our industry very much engaged in how concrete works and how it's designed. But concrete's been around for a very, very long time. You know, I've had the pleasure of kind of visiting a few of these sites, including the Roman Pantheon, just a couple of years ago. An unreinforced concrete dome, the largest in the world, built almost 2,100 years ago. So these are neat concrete structures that are all around us. And here in the United States, the Federal Highway Act of 1956, what would then become our interstate system, called for 41,000 miles of concrete pavement to be laid at a cost of about $41 billion. It's substantially a lot less than what it would cost today to build that same amount of highway. But 60% of that work was constructed with new type concrete, as was done in the advertisement that you see on the screen there. Some of the other things maybe a little closer to home, for those of you who are up here in the Midwest, if you'd like to go see where is the oldest concrete street in America, George Bartholomew in 1891 posted a 5-year bond guaranteeing the performance of a small street that he was going to pave with this new type of paving system in Bellefontaine, Ohio. That pavement is still there today, and although there's some repairs and work, the original concrete, now almost 130 years old, still in good performance. So we know we can make concrete, we know we can make it well. There's also other concrete firsts that are in the Midwest. The first concrete skyscraper in the world, 15 stories, built in Cincinnati, Ohio. In fact, when they constructed this, the scaffolding that was on the building, when they were beginning to prepare to remove that formwork, they had to evacuate the lower streets below because there was concerns that it was going to collapse. And that structure is still there today. It's actually undergoing a major renovation right now if it hasn't been completed yet. Lots of things in our part of the world that show the versatility of concrete, including structures such as the Hoover Dam, built in or started to go under construction in 1928. 20,000 workers worked on this structure with wages up to about $1.25 per hour. Again, very different from what we see out there today. But 3.25 million cubic yards of concrete went into this structure. And you can well imagine the environmental conditions for those of you who have been to the southwest corner of the United States, the heat, the conditions in what would be an area just outside of Boulder, Colorado, you had to work under. Again, a structure that's still well in place today. But when we look at what's happening globally with structures like this, 3.25 million cubic yards of concrete dwarfs in comparison to what is now today the largest dam in the world, the Three Gorges Dam on the Yangtze River in China at 35 million cubic yards. So I'm sure there's a lot of precast producers that are out there watching this webinar today that would be very happy to have a contract that called out for 35 million cubic yards of concrete. But we don't see that a lot in precast. A lot of the structures that we build are generally a little bit smaller, but there's still a lot of cool concrete that is out there. I have not had the opportunity to go see the Sydney Opera House in Australia. I hope to one day, but this structure is actually comprised of precast concrete shells sitting on top of 588 concrete piers. Speaking of piers, the Petronas Towers in Kuala Lumpur, Malaysia. This is the world's deepest foundation system, 375-foot piles on the concrete raft on those piles at 15 foot thick and another 17,000 cubic yards of concrete. So when we talk about concrete, we talk about large structures, we see these kind of neat things, but reality is it can be used anywhere. And this is an industry that is beginning to come back in popularity, whether it be due to the cost of lumber, but concrete construction, resiliency, it's a word that the NPCA has used quite extensively over the last while. We can build concrete homes. In 1908, actually, Thomas Edison designed and built the first concrete home in Union, New Jersey. And these structures are still in existence today. And 100 years later, we're starting to see the use of concrete, both cast in place and precast, used for structures. So at the end of the day, concrete's everywhere. And concrete will continue to be the dominant building material of the future. There's some sustainability angles, obviously, that are becoming very prevalent in the discussion today for what concrete is doing. And we'll get into a little bit of that as we kind of begin to discuss what fiber reinforced concrete talks about and how that can contribute to a better, more sustainable, a greener, or a more environmentally friendly construction environment. So let's get into the discussion we're going to get into today, and that's the use of fiber concrete. And if you have attended any of these fiber presentations that you see from any of the producers or the manufacturers of fiber reinforcement products, you generally hear about these slides talking about how fibers have been used since Roman days, straw, mud bricks using hair, anything that can be doing, anything that you can put in cementitious or building products to reinforce parts of the material, whether it be to cut down on cracking, whether it be just to make a more cohesive material. And we saw this in the use of stucco pretty predominantly in the 40s and 50s. The Roman engineering that you see from over 2,000 years ago used a lot of, again, horsehair and straw in their mud bricks, and it kind of moved into early residential and pioneer construction. Today's fiber reinforcement industry is very different, and it is a very big business. Really through to the 1960s, there was very little agreed on research, and a lot of that had to do with the academic research that took place with fiber concrete, but there was very little agreed on approaches. And many of the marketers of fiber reinforcement would go to market and have a product and get a limited application or get some form of success and just run with it and say that my fibrous material can be used to replace wire mesh with very little backup. That wasn't until now. Over the last decade, millions of dollars of research have poured into various academic institutions, universities. Department of Transportations have investigated the use of fiber reinforced concrete, and the knowledge base and the quality of technical individuals that are employed by these companies distributing fiber has improved dramatically. And so we're now seeing design guides, we're seeing codes, we're seeing a lot of applications and successful installs of fiber reinforced concrete throughout the the ready-mix concrete market, the precast concrete industry, and the shotcrete markets, to which case fibers are now being considered as reinforcing. And when we talk about reinforcing, we need to make sure we talk about what that is, because we're not using fibers today to replace steel in columns and in primary reinforcement for decking systems for large precast shell structures, but fibers can be used in different applications to augment or to, again, reinforce concrete. But the design documents we have today kind of help guide us through what they can and can't do. So when we talk about why fibers can be used in concrete, or why should we use fibers in concrete, there is a short answer, and it applies pretty much to any type of material that's out there. We want to control cracking in concrete, both during the plastic and in the hardened state. And the type of fiber, the shape, the amount of fiber that goes in there will dictate the response of that concrete. We can actually put enough fiber in concrete today to make a concrete matrix that's actually stronger post-crack than it is before cracking even takes place. Those are extreme examples, but it can be done. The issue we have at stake is, as many of us know, concrete is strong in compression, but weak in tension. So we need to reinforce it if we have to get in any flexural type loads or moment designs or situations where concrete could potentially crack. If it does crack, we need something in there to hold it together. The traditional market's always been rebar or wire mesh or some form of composite reinforcing. But with today's fiber industry, we can look at the possibility of using different types of fiber to reinforce concrete. And in the precast market, what we want to do now is target some of those applications. And many of you on this webinar are probably familiar with these types of structures, whether they be riser sections, tanks, steps, chimney sections, flared ends, pipes, curbs. What the reinforcing is required to do in those structures is just as important as the amount of fiber that will go in there to satisfy any form of engineering requirement. Some of the other opportunities that exist for us in fiber concrete situations, again today, and our market is changing, includes precast paving slabs, which the National Precast Concrete Association has a subcommittee on, the use of utility and junction boxes for our infrastructure, something that should be very popular over the next few years, especially if our current administration moves forward with an infrastructure package. We should see a lot of precast concrete used, again, from a durability and a longevity standpoint. MCP, or manufactured concrete products, tilt-up construction, wharf and marine structures, primarily for durability, and things such as sound walls should all become good opportunities for the use of fiber reinforced concrete. So getting back to now, what is fibers and what types of fibers and what are the uses of fibers? We need to understand various components of what these products can and can't do. We want to make sure that we understand the benefits to the contractors, to the engineers, to the owners, and obviously the precast producers. These fibers that are in the marketplace today can reduce construction time. They can possibly be a more economical alternative if the engineering is required. And as the industry moves forward, and it will and continues to change as it's done, we'll see more types of code approvals, and we'll see a continued track record of success going forward with our market. It's important at the end of the day, though, to understand that all these different types of fibers have different impacts on the workability and the final properties of how concrete's going to flow, place, consolidate, finish. So it's very important that we understand what those fiber types are and understand the rheological impacts on using them in a concrete mix. Today in our marketplace, we have many different fiber types. We have different materials that are available. And if you look at just the ASTM C1116 designation for the use of fiber reinforced concrete, it will generally drive those down into 4 primary categories: steel fibers, synthetic fibers, natural fibers, and glass fibers. For the purpose of this presentation today, we're going to talk primarily on the use of steel and synthetic, and then drive that down a little bit farther and talk about macro fibers, steel macro fibers, synthetic macro fibers, and microfibers, which are primarily in the natural and the synthetic industries. Those microfibers, and many of you may have been around for more than a few years, those fibers are generally used at low dosage rates to control secondary, some people refer to it as secondary, but plastic shrinkage cracking. The secondary term is a little bit loose, but in the most part, these types of fibers, these microsynthetics or natural fibers like cellulose or polypropylene, 3/4 inch, 1 pound per cubic yard, those type of applications are generally putting fiber in concrete not to add any load carrying capacity or structural capacity of the concrete. They will not alter the strength of the concrete. They will not alter the flexural response. But if we start using steel macro fibers or synthetic macro fibers in industrial floor designs or heavier replacement of conventional reinforcing, these fibers, the 2 photos you see on the bottom right, these steel or synthetic macro fibers, kind of act in the same capacity in that they can hold concrete together in the same way that conventional steel holds concrete together. The dosage rates that those fibers would use should always be calculated by engineering requirements. There is no one size fits all for these types of fibers. Dosage rates on the steel fiber can vary all the way up to 100 pounds per cubic yard if you're using things such as slurry infiltrated fiber concrete, or if you're going to use a synthetic macro to be equivalent to a wire mesh, 3 to up to 15 pounds per cubic yard, or just under 2 kilograms to 10 kilograms per cubic meter. If there's any people who use the metric system on our webinar today. The benefits of these different types of fibers, we'll get into the type of fiber that you use, but overall, if we can reduce labor or construction time, if we can improve safety on a job site, for the flooring industry, they're looking at things such as reduction in thickness or reduction in joint control joint spacing. And then afterwards, obviously, in service is just as important because the owner generally does not want cracked structures. By using fiber concrete, they're going to get into a more three-dimensional as opposed to two-dimensional with steel. Any cracking that does take place with fiber concrete tends to be shorter and thinner. That can lead into waterproofing and weatherability type applications or advantages. Fiber concrete can lead to less spalling, chipping, increases in long-term durability, and then all of that will generally lead to lower maintenance costs. So again, coming back and knowing which of these benefits you're going to get into by the types of fibers, it is very important to understand the typical fiber types and dosage rates that we get into. Synthetic microfibers, as I mentioned earlier, 0.5 to 1.5 pounds per cubic yard, or 0.3 to 0.9 kilograms per cubic meter of concrete, generally only used for plastic shrinkage cracking control. That's the cracking that takes place in the first 12 to 24, maybe 36 hours as our concrete dries, loose term, but as it's initially going through that hydration curve and we lose moisture, any cracking that might take place can be arrested by the use of these smaller fibers. There's other types of synthetics out there, generally referred to as fibrillated polypropylenes, maybe a little bit of an older technology, but a little bit higher fiber counts, more of a net type of fiber. You can use those types of fibers at a heavier dosage rate, the 1.5 pound or close to 1 kilogram per cubic meter, to replace 6x6 10 gauge wire mesh. Understanding though that those are only in situations where that 10 gauge wire mesh is generally used to control, again, the same temperature and shrinkage or plastic shrinkage cracking. 10 gauge wire mesh will not provide any additional moment or structural control, neither will the microfibers that you generally put in concrete. If you are looking for that type of reinforcing, you would generally get into the steel or the synthetic macrofibers at dosage rates that are typically elevated with engineering tools to determine what those dosage rates may be. For the synthetic fibers, the monofilament polypropylene or blended fiber systems, generally 3 to 20 or 1.8 kgs to 12 kgs per cubic meter. You can get into temperature and shrinkage crack control applications. You can get into structural applications. You can exceed modulus of rupture of concrete with these high dosages of fibers. Same for the steel fibers in the 15 to 100 or approximately 10 to 60 kgs per cubic meter. These engineered calculations following the principles of ACI, which we're going to go through here a little bit, generally will be signed off on by engineering firms or by in-house experts that would be employed by the fiber reinforced producers or within your own precast organizations. Those performance metrics are becoming much more prevalent in today's industry, and we're seeing a lot more specifications that are written around performance requirements, and those performance requirements can be vetted through various types of ASTM standards for testing, and specifications will generally read terminology such as residual strength or toughness factors. Those specifications can call out brand X by manufacturer Y with Z pounds per cubic yard or kilograms per cubic meter. You know, dosage rates of fibers, again, are not one size fits all. Very similar, and you can think of it this way in terms of different types of rebar, grade 40, grade 60 or higher rebar, or typical strengths of wire mesh or composite rebar. There are many types of fiber products on the marketplace, all with different properties. So it's very important that we boil these down to common performance metrics, such as the terminology that we're using today, residual strength. In order to understand what those residual strengths and the terminology that's being used, the American Concrete Institute, or ACI, has really done a wonderful job over the last 5 to 6 years to build a new library on how to use fiber reinforced concrete. I've been a member of this committee for several years now, and it's been exciting to see some of the new documents, especially the 4R, 5R, 7, 8, 9. These are all documents on the use of fiber reinforced concrete that have all been published all inside the last 5 years. And there's currently revisions going on to other documents in the library that is used for fiber reinforced concrete. Committee 544 is the ACI committee for fiber concrete. There are over 100 members globally that are supporting the use of how to get the design tools, the specifications, how to proportion, mix, place, the fiber types, etc., into the hands of users, including the precast concrete industry. Outside of that, looking at some of these other documents, whether it be for floor design, contractors, ultra high performance concrete, shotcrete users, again, fiber reinforced concrete will show up in many of these documents. But for today, I want to focus on the 544 4R document, which was published in 2018. This is a guide intended to be used by designers who are familiar with concrete, specifically structural concrete, but may need more guidance on how to use fiber reinforced concrete. In this document, fiber is treated as reinforcement. It's not an admixture. Fibers are used or placed in concrete to be used as an alternative to conventional rebar. And this document will guide the users in terms of how to use the fibers, how to select the fibers, and then it'll also get into some specific details on applications and construction practices. So this new approach for FRC design talks about some of the terminology that we've already approached today: microfibers, macrofibers. It talks about some of the testing, the evaluation methods, and broke away from a previous document that really focused on the materials and what they can do. Chapters 1 and 2 and 3 kind of get through the old document and talk about the characteristics, the definitions, the history. Chapter 4 now gets into the design and how do we take a two-dimensional, conventionally reinforced concrete element or section and replace that 2D reinforcing with a bunch of toothpicks or a bunch of sticks in concrete that are now three-dimensionally through, and uses published research from the academic community over the last 20 years to get us through in terms of how fiber reinforced concrete can be treated the same as conventionally reinforced concrete. So when we look at that document overview, there is basic information. This is a good starting point. This 544 4R document can serve as a jump off as well to other documents depending on who the user may be, and then gets into the engineered design and calculations. And one of the core pieces of this is a testing setup, ASTM-C 1609, that is primarily used to do two things. One, compare different types of fibers that are on the marketplace under the same conditions, but then also determine what is the residual strength, and that's the terminology that you see on the screen here. This is a 4-point bending test run under very controlled, specific applications where we take concrete, we crack it open, and then we measure how fibers resist the load or prevent that concrete from cracking farther. Whether you have a slab on grade or a precast piece of concrete that's resisting earth and pressure or has to do with water tightness, we can then find out what is the crack width we wish to evaluate that concrete under, or what is the loading that that concrete may be subjected to, and make sure that the fiber is providing the engineering performance that we need to resist. The way that works in the document, and not to spend an entire presentation going through engineering detail, but when we look at our conventionally reinforced concrete with steel at a set location, we can determine what the capacity of that steel is through a very engineered stress block and calculate what it is that the steel is doing. If our precast concrete element is designed with steel to resist specific types of loading, we can then determine what that steel does and convert that over to a fiber reinforced concrete equivalent and determine what that stress is needed. This formula can be broken down in a very engineered or Excel spreadsheet, or there's various web apps that are on the market to determine how we go through a solved example. So for this particular application, I'm going to take an 8-inch precast panel reinforced with number 4 rebar at 16-inch on center, with that steel placed directly down the center to provide bending moment resistance in either direction. What we need to do is find out what is the residual strength requirement so that the fiber reinforced concrete can provide the same level of post-crack capacity that the rebar section. So when we plug in the numbers, 5,000 PSI concrete, grade 60 steel, and again, knowing exactly where that steel is located, that's very important. That'll allow us to determine what is the capacity of the steel at 31,000 pound inch. We can then determine what the capacity of that fiber reinforced concrete section has by sticking in the exact same moment requirement, the section properties, and determining through various factors that I need to resist 270 PSI of moment resistance. I can then take this solution to the various fiber manufacturers within our industry and ask them to provide documentation for their fiber brand X to meet this engineering requirement Y. Where would you take this to? Well, there's various laboratories throughout the United States and in Canada that can provide testing services. And again, this is important that you understand that when we do testing, they need to be in same mix situations. Concrete mix design needs to be consistent, and we need to ensure that we are testing under statistical properties, that we have enough validity or enough statistics to our concrete mixes to be sure that that fiber mix can be meet those engineering requirements. So that's kind of the background on where that ACI document comes from and how it works, and in terms of how you can take that to your fiber producers and have them do an evaluation for you. The additional topics that show up in this document, not to spend a lot of time on this part, but the 544 again goes for our document again, goes through some additional discussion points, because obviously putting high volume fibers can have an impact on the concrete mix design and the workability. How we place and add fibers into concrete mixtures is important. For the precast industry, generally we have short mixing cycle times. We have difficulty in finding an opportunity to add fibers to concrete, and there's a bit of discussion topics that are in this document to help you go through that. How we place, consolidate, finish fiber reinforced concrete, quality control, and in the flooring industry we'll talk about control joints and how we can specify fibers going forward. I'm going to break into a few of these topics just specifically because I think it is important that we discuss what type of fibers are being used and how they can have an impact. Obviously, there are different methods which will have different costs in terms of how to add fibers to concrete. If you are in a central batch plant and you have the ability to add fibers directly to an aggregate source, that might be the fastest way to get in there, but it can have impacts on cost, etc. Speed, safety, the types of fibers, the amount of fibers, the job type that you're working under, the specifications that are necessary in terms of how to add fibers can all come into play here. So it's important that these discussion points are all brought up before we just start adding fibers to concrete. Adding fibers to mix designs that are not supportive of putting high volume fibers can be problematic. So even if you solve the issues of how to add and mix your fiber, if your concrete mix design is not accommodating to a fiber type at the beginning, you can have problems and, as the expression goes, leave a bad taste in your mouth. So again, like in the flooring industry, a pre-job or some form of a discussion prior to how you're going to add those fibers might be important. As is also what you're going to do after the fibers are in concrete: placing, consolidating, finishing. For the most part, our industry looks at this, that fiber reinforced concrete can generally be finished with similar tools as used for unreinforced concrete. And then also with that, it's important to note that fibers are not a substitute and should never be used in applications where concrete's not adequately cured, or where we're going to be worried about humidity or temperature. They are not a cure for those problems, but they can help. It's such as these suspenders and insurance type discussion that sometimes comes up. Fiber reinforced concrete will be more cohesive than ordinary concrete, so you will see differences in finishing, especially if you're doing textured finishes. Again, it's always recommended in any application, be it precast or flooring, that trials would be recommended to ensure that you are adequately prepared for what concrete looks like and what concrete's going to finish like. Sometimes finishers will see fiber reinforced concrete be more cohesive. They may get their timing off because they think concrete is setting up quicker. But for the most part, fiber reinforced concrete should be finished, should be cured under the same conditions that you would do ordinary concrete. In terms of some of the problems that do exist in the industry, these would be some of the common mixed design issues when we use fibers. Over the last 25 years, we've seen lots of errors made, not so much from problems with the fibers themselves or the mixed designs, but most likely due to unfamiliarity with how to use fibers in concrete. The biggest problem that you can run into, especially when using high volume fiber reinforced concretes, would be insufficient cement or fines to coat the extra surface area of those fibers. Fiber is like an aggregate. It needs material, paste, to be coated onto that. As we pull more paste away from the mixture, that's less fluid concrete that we have to help concrete flow. So whether you would increase fines or find other ways to offset that workability of concrete is very important. Again, coming to the point of a trial, using chemical admixtures, never water, to ensure that we have the correct slump or flowability, and water obviously would alter strength and other durability aspects. Batching of fibers, we saw that slide earlier where they were adding fibers into concrete trucks or into batching systems, into mixers. We always want to be sure that we're not putting fiber into a zero slump condition. Typically, fibers need to be distributed through the concrete. They're usually introduced in a much tighter sequence, such as in bags. We want to be able to distribute those fibers through the concrete. In a zero slump condition, that would have a tendency to have fibers ball much more easier. So again, it's important to talk to your manufacturer, your fiber distributor, to ensure how they would recommend adding fibers into your concrete. We want to make sure that we evaluate fiber concrete the same way we evaluate ordinary concrete, with probably one exception, and that's the slump cone. Fiber concrete will make concrete much more cohesive. So a slump cone may not be the best indicator of workability. Usually under flow is what we're looking on. And most precast producers, I know many of you do here, would use self-consolidating concrete. So that generally will not be a problem both for the zero slump condition and for the workability condition. But either way, finishing techniques, timing of finishing as well, would be relatively important points to discuss when looking at fiber reinforced concrete. That said, all these little adjustments, all these tips and tricks within our industry are generally, and the way that our world works today, is one click away as opposed to one phone call. The fiber manufacturers and the Fiber Reinforced Concrete Association, which many of the manufacturers of fibers are members of, have various technical guides, tips, tricks, recommendations on how to work with fiber reinforced concrete, again, specific for precast applications, adjusting those mixes for high volume steel or macrosynthetics, how to do finishing practices, especially if you have exterior decking systems like double T girders or precast paving slabs, how you would finish those. And again, making sure we understand how to navigate all that technical language and the various test requirements that are out there. I like to think of specifying fiber reinforced concrete in two simple ways. You're either going to use fibers for shrinkage and temperature crack control, to which case you would primarily use microfibers, maybe some steel and synthetic macrofibers at low dosage, a couple of standards that are out there to evaluate, and then specify it whether you're looking at percentage in crack width reduction or just familiarity with regards to knowing you have a better product, less chipping, less spalling. If you're looking for post-crack or tensile or flexural capacity or equivalency to conventional reinforcing from an engineered or moment perspective, generally we're looking at a couple of ASTM standards. For the precast industry, that would be that 1609 standard you see there, and we would be looking at terminologies again such as that residual strength or toughness. Here in the US, we would use that ASTM C 1609 standard. Some specifications that come from overseas would use the European 14651 standard. That's another beam type test with a notch that's in it. We're starting to see many of those types of standards used, especially for precast tunnel segment linings, where different evaluations or different engineering is being used. But at the end of the day, they are all measuring that post-crack performance. Many manufacturers of fibers can assist through that now. Various mobile apps are available to determine whether you are using temperature and shrinkage or bending moment design. These apps follow the ACI formulas. They provide the calculations. They provide the numerical values that would help your engineering teams to determine that they have the correct amount of fiber reinforcement in there. Many of these apps also will allow you to determine the cost and will be used for submittal purposes. So you can determine what is the fiber dosage, what is the cost of that fiber alternative versus steel, fully installed, whether through your mixer or through if it's supplied by a concrete producer. And you can take that as a submittal document to the engineer, and it can be done very quickly. These apps nowadays can provide those equivalencies in just a matter of seconds if you know the existing reinforcing that's in there. In the flooring industry, there are additional tools now, so we are no longer converting existing steel over to fiber designs. We are actually now able to design fiber from scratch, and this will be coming to the precast industry fairly soon. Where this is all leading to is the use of specifications. I mentioned this earlier, that specs are now being written with fiber language calling out sometimes mixed designs, but when it comes to fibers, they are calling out the performance requirement. Another analogy I like to use when it comes to this is we typically in our industry don't see minimum cement contents or minimum air contents if we're looking for durability. It will call out specific strengths for concrete design, whether it be compressive or flexural, and then an air content, it will require a 6% plus minus 1 for freeze thaw durability. The fiber industry is going in that direction as well. We are not calling out manufacturers. We are not calling out dosage rates. We are typically putting in a residual strength requirement. From there, you can call out test names or fiber dosages specific to individual manufacturers. But this will become the norm going forward. And so to many of the precast producers that are here, I would recommend just to get educated in terms of what those languages are. And again, talk to your fiber manufacturers in terms of what they can provide for dosage rates to be used as alternatives to conventional reinforcing, and how they're going to back that up with solid engineering and test results. So where is this all going to? This was kind of the history, the ACI language, the technical, these methods are now in practice. And if you look across our industry now, many DOTs are developing what we would call qualified product lists, QPLs, performance-based specifications, most of it for paving and flooring today, but it is coming into the precast industry. And I'll show you a few applications of those shortly here. But we're seeing project specifications on the West Coast, in the Midwest, on the East Coast. That ASTM C1609 beam test is becoming the go-to standard for fiber performance in floors and precast, and the design methods and specs are now referencing these test methods. So at the end of the day, what this all means is there are now codes, there are now guides, there are now standards that are primarily leveling the playing field for fiber reinforced products that are out there. No longer are they going to be relying on questionable marketing terms, glossy brochures. It's going to primarily be more of a technical design approach, and ready-mix and precast concrete producers will generally be protected by the engineering support staff that they would get from the fiber reinforced concrete industry. As we move into precast now, and we talk about the applications of where fibers can now be used in fibers, we want to talk about environmental structures, rainwater collectors, wastewater tanks, septic tanks. We'll get into that in a little more detail here shortly. Oil separators, we look at vaults and storage bins, burial vaults, lawn crypts, transformer, cabins, boxes for light pole bases, storm shelters, transportation structures. Obviously, if this infrastructure package comes to the forefront of our industry, we could be looking at a substantial market, a very high growth market in new transportation structures such as railway sleepers, which more than likely would be hybrid, but fiber reinforced concrete could offer some durability angles, jersey barriers, wall systems. Wall panels are actually now becoming very popular for retaining walls, sound walls, seawalls, facade panels. And then in the mining and tunneling industry, segmental precast tunnel linings. This actually, with the ACI 544, I believe 7R document, I want to go back and check that, but that is now allowing for the use of fiber reinforced concrete to be used in these precast tunnel segment linings. And again, this will most likely become a very large growth opportunity in the near future, especially here in the United States, for precast tunnel segments. But remember, through all of this, the opportunities that do exist in fiber, you know, we're not coming to the marketplace to replace all steel. Fiber does not necessarily need to be used as a complete replacement to conventional steel. We do know that many producers who have begun to use fibers have commented back that less chipping and spalling, certainly less plastic shrinkage cracking, less callbacks, better durability, more consistent product performance. Those types of concrete applications can lend itself well for marketers in terms of being able to go to the market with better quality products. I like to talk about a few of these pictures in terms of some of these applications that I've been directly involved with. This lower left photo, those are precast concrete baseballs. This article was actually featured in an article in Precast Solutions magazine many years ago outside of Greensboro, North Carolina. Those structures are 5-foot diameter, and the fiber reinforced concrete alternative that was able to be used for these was actually born out of the fact that it was going to be very difficult to place wire mesh to reinforce these structures in that spherical position and not have any ghosting or any type of wire mesh showing through. So a fiber reinforced concrete alternative was done by the manufacturer, and these baseballs are still there today. If you ever get the chance to go watch a baseball game again, and I know we all will, but if you get a chance to go see the Greensboro Grasshoppers baseball stadium, you'll see these structures just off the right field corner there in Greensboro, North Carolina. Most of these structures, such as the walls on the right, and again, we mentioned septic tanks and sewer pipe, underground structures. Again, fiber reinforced concrete, the less chipping, less spalling, doesn't necessarily need to be for above ground. It can be for below ground structures too. And the way that these concrete applications work will dictate how much fiber needs to be used, or whether you wish to use a hybrid system again, especially in tank structures where there may need to be more steel and lids to support HS20 or HS higher vehicle loading that goes on those. You may want to consider the use of fiber reinforced concrete in the bottoms and the sides and keep a hybrid system in the lids, again, to give a better structure. And in terms of, if anybody here is thinking, well, I'm not sure if I want to see how long or how much service these have had, what's the history here? In 1997, I'm trying to do some searching for this. This may have been possibly the first septic tank manufacturer in North America to incorporate macrofibers in complete replacement of all steel. And this was in Nova Scotia, Canada. And I know part of this story because I'm standing on the tank in the right-hand photo. But a local university, a local engineering firm, a precast producer all got together to look at an alternative. And we had to do a multitude of testing, water tightness tests, load-bearing tests, serviceability tests. It took 3 years to receive the governmental approval to sell fiber reinforcement in these 1,000-gallon residential. I believe there was some 1,500-gallon tanks here as well. Today, that manufacturer is still using the same fiber to reinforce their tanks. Much of the research that was used on these tanks kind of went into some of the formulations that still exist today that came out in the 544 4R document. These dosage rates were higher at the time, obviously, because we needed to be far more conservative. But it is very interesting that this sort of maybe served as the foundation for where we're seeing fiber reinforced concrete used in many of the precast structures today. The dosage rate, if you're interested in these tanks, was close to 10 pounds per cubic yard at the time, just under 7 kilograms per cubic meter. I believe they have reduced that based on the new codes and design applications that were out there. But if you look at septic tanks as a whole, These are thin wall concrete applications. Knowing where your steel is located is important. Knowing that you may need to have steel in corners and lids is important. But after that, if we can increase the speed of fabrication, there is no steel to cut or place. We have no steel machines in-house. We have less reinforcing to install, to inspect, to chair. And you combine this with chemical admixtures to create flowable or self-consolidating mixtures. You can not just save economics, and if that's what you're looking at only, in terms of the cost of materials, but you can save time, which obviously there is a value. Other things that some precast producers have commented back is with less steel equipment, less cuts, less insurance, less healthcare costs. Obviously that's something else. That all leads to safety. So can we create a safer, more economical, and a green environment? And we'll talk about that in just a moment as well. Some of the other project successes we've seen using fiber reinforced concrete over the years is lawn crypts or burial vaults, septic tanks, again mentioned, approved across the country of Canada through a CSA, Canada Standards Association. The B66 document now permits the use of fiber reinforced concrete with a residual strength requirement. Georgia, Virginia, Michigan, Florida, many other states have all got various forms of QPLs through the Departments of Health or Departments of Transportation to use fiber reinforced concrete. I mentioned the lawn crypt or burial vault type structures. Again, what we want to do here is establish the structural performance, the reinforcing requirements that exist. We want to perform those calculations. We want to verify that mix design and then test to various requirements, which for most of this industry would be vacuum testing or water tightness tests. I mentioned before there's other applications that might be hybrid. When we look at something that seems to be becoming very popular today is these wall or sound wall applications. In these applications, sometimes steel is required in the columns or when the panels are transported. If they're not cast in place, obviously they're generally going to be precast. When we lift these panel structures, especially following demolding, we may need additional steel in and around the corners or around the perimeter of these types of applications. And then fibers can be used for the temperature and shrinkage stress or to replace the lighter amounts of reinforcing. Now, there might be structural considerations here. There could be wind loads, such as in hurricane zones, but most of those calculations now are very easy to determine based on the ACI type applications we just saw. We want to look at these applications one project at a time. And as every producer on this call would know, every precast product has its unique challenges in terms of casting, its mix designs, its molding. If you take a look at this structure in Virginia, this is a stormwater retention system using an underground precast baffle system. These structures, which are about 6 to 7 feet in height in the top right-hand photo, are reinforced exclusively with about 10 pounds per cubic yard of synthetic macrofiber. Once this structure is in place, most of the mode of loading does go into compression. So certainly we don't have a lot of flexural, but when these panels were handled, when they were moved around in the yard, we wanted to ensure that the fiber reinforced concrete would be able to withstand the same amount of stress that a conventionally reinforced concrete application would have. So these are, again, kind of one-on-one discussions with your fiber engineer to determine what is capable and what is possible with fiber reinforced concrete. Now, let's discuss some of the things that fibers can't do, because there are some myths and there are some facts that are out there, but for the most part, fibers do not change the compressive or the flexural strength of concrete. And as a designer myself, flexural is far more important than compressive, although compressive is typically what's supplied. There are some producers in the marketplace that will claim that their fiber changes the rheology, and there are products that are in the marketplace that can do that, primarily more on a nano or microscopic scale. These are much more expensive, much more high volume fibers, but for the most part, that 90% rule or 80-20 rule of the majority of fiber markets, products that are on the market, they do not change the strength. All fibers, whether they be steel, micro, macro, synthetic, etc., have the potential to ball or clump. And that's the generally speaking, the number one complaint that comes back from producers who aren't happy with the use of fibers. How you add those fibers, introduce those fibers, how they're packaged and added into concrete, how you sequence that in your batch process that'll all play a key role in determining how fibers work in concrete. One of the myths that are out there is many producers will talk about how longer fibers or steel fibers are difficult to pump and place. That's not necessarily accurate. Again, the key lies in the mix design itself. There are synthetics that can go through very narrow openings, generally because they're pliable or less rigid type fibers, and macro synthetics and steel fibers, for that matter, have been very successfully pumped, placed, and shot for the shotcrete industry at dosages all the way up to 15 pounds per cubic yard or 9 kilograms per cubic meter. Again, talk to your producer, they'll guide you through that. In terms of what many of these producers, though, do, it's important to understand the engineering liability that's out there. Many producers will come to us and ask us to sign off or stamp. Most concrete fiber producers will generally have engineers on staff, but it's very difficult for them to stamp or sign off. You are best off, and the National Precast Concrete Association has very good liaisons with engineering firms that will support the use of fiber reinforced concrete, and that they will be able to help you through that. The engineers who are on staff at the fiber manufacturers will generally interface with either your engineer or the engineering firms that are out there to support the products and support the engineering and show where the design codes are now permitting the use of fiber. So this is an important aspect to understand if you're just going to swap out steel for fiber, or you're going to design with fiber. Who ultimately becomes responsible for that? The engineers, again, that are on staff at these manufacturers will certainly assist you in terms of how to get through that. Obviously, the one thing we've stayed away from through a lot of this conversation, but not on purpose because we're going to talk about that now, is the cost. And it's also, again, very important to understand when you're discussing fiber reinforcement versus conventional reinforcement, or different types of fiber reinforcement from brand X to brand Y, it's not the price per pound that really matters, but it is the price going into your unit per tank or per cubic yard or cubic meter of concrete. When you look at performance applications, the amount of fiber that goes into that tank or into that wall system and how that compares with speed, with cost of fiber, with other ancillary labor, those are all things that you need to take into consideration. So it's very important that we understand the cost per tank at the end of the day out the door when we look at a fiber reinforced concrete solution. There are different methods that are out there, and I want to show just one real quick example just so it's understood that this isn't a complicated process. But if you have a 6-inch thick concrete section reinforced with 4x4 4-gauge mesh, reinforced at 2 inches from the top of the slab or 2 inches from one side or another, we have a amount of steel in that section that would be a row value or a reinforcement area of steel or area of concrete at 0.8%. Anything below 0.1% in our industry identifies that that steel is primarily there for the use of temperature and drying or shrinkage crack control. Fiber brand X with a dosage to match, let's say it calculates out to 150 psi residual strength. Many of the macro synthetics would be at about 4 pounds per cubic yard, or potentially somewhere between 20 and 25 pounds per cubic yard of a steel fiber. What you would then do is take that 4 pounds over the 54 square feet per cubic yard that you get, multiplied by the price per pound of fiber. That's going to give you your cost per square foot. And obviously you're going to need to work over your thickness. You change the thickness, it's going to change your cost per square foot. You change the length of your wall, you remove now your steel, you take a look at everything you want to do there to make sure you're comparing apples to apples. So what we want to do is ensure that we compare this to the fully installed wire mesh option that is in place. Something that's become very prevalent in our marketplace now also is sustainability. And I'm not to do proprietary, but I just want to show off something here very quickly because many of the fiber manufacturers are now investigating this. In 2012, 9 years ago, the company that I work for funded a research project to establish what could potentially be the savings in greenhouse gas emissions associated with replacing steel in fiber concrete applications. And this was for a cradle to site type application, looking at shipping distances of remesh or steel versus fiber. And it showed that fiber reinforcement versus steel reinforcement will generally save in terms of that greenhouse gas emission. But that's on the fiber side only versus the steel. It doesn't include all your concrete. In the flooring application that primarily was brought up for this particular study, it showed that it was able to reduce the GHG or CO2 equivalent by about 4%, which can be significant if you're building structures that have any type of LEED requirements, or you're looking for any type of environmental angle to promote or market your product. We always want to talk to that not all applications would necessarily be suitable to the use of fiber reinforced concrete. Again, potential testing is required. We want to review the technical and engineering merits before touting any of the marketing advantages. A lot of steel would require a lot of fiber. A lot of fiber may not necessarily be in your best interest, especially if it would be difficult to mix and place. And sometimes you may need to test. And this is a really neat application that, again, that I was involved with two different producers. If they need to have an engineer take a look at a wall system to determine what is the load carrying capacity of a fiber reinforced hybrid or a fiber only solution. Did you know that a 5-gallon bucket generally will take up about 1 square foot of space? So if we were to take a panel, a wall system, and put a series of 5-gallon buckets across that, we could then fully load those buckets and get about 40 pounds per square foot loading on a wall, which might be equivalent to a category 1 or category 2 wind loading. So would this particular wall that you see in the photo here, when stood vertically with a fiber reinforced concrete solution, be able to withstand the wind loading that would be brought on by a hurricane force load? What's interesting, if you can see on the photo on the right hand side, this is actually taken from a video, is we over exceeded the capacity of this panel section. It did have a piece of perimeter steel located in this 6-inch wall section. But what ended up happening is we developed a series of micro cracks. That panel is actually bent like a smile. And what we were able to demonstrate for the engineer here is that even though we began to exceed the cracking moment or the flexural modulus of rupture of that concrete, the fiber reinforcement would then engage and prevent that concrete from going into a catastrophic or very large debris type failure. In fact, that panel did not fail and was able to be removed and replaced following the test. So what does this all mean? We're going to summarize some of this presentation up here over the next couple of minutes. And what we have now is a situation with fiber concrete that we have new design tools. We have specifying horsepower. It's now becoming a fair game with the same set of performance criteria. And as an industry, we need to continue to go out and educate both the ready mix, the precasting, the contracting, the engineering community. And the fiber producers are going to continue to work with ACI committees. They're going to continue to push. They're going to continue to demonstrate where we've been successful and take a look at new applications. The National Precast Concrete Association actually has a couple of resources available to you. And if you go on to their resources page, you will see that there is both a tech note and a white paper on the use of fiber reinforcement for precast concrete applications. Also, many years ago, actually dating back to 2005, the Best Practices Manual, this was first published in 2005, has a section on the use of fiber reinforcement and actually uses the correct terminology in terms of macrofibers and microfibers and discusses how it is possible to use fibers as a replacement for conventional steel. It goes through many of the parameters that we've previously discussed here over the past hour in terms of being sure that you have the correct fiber, the correct dosage rate, and the correct mixing procedure. The tech note that exists today with fiber, with NPCA does discuss very similar points that you see in that 544RR document: fiber types, mix design considerations, batching, mixing, sequencing, how to avoid balling, how to add those fibers, the batching systems that exist today, and how to consolidate, trowel, dealing with bleeding, how to finish, correct floats, and has a short section on the use of stainless or galvanized steel fibers, which are also becoming relatively popular in our industry. The white paper that exists as well by NPCA is a couple of years old now, gets a little bit more detailed into fibers and kind of talks maybe, again, similar to that 4R document from ACI 544, maybe what's in more of those first couple of chapters. What is fiber reinforcement? How do fibers work in concrete? How fibers can be used in precast manufacturing, mix design, production, and how to test, again, which is very important with all the fiber types that are out there today. Other resources outside of NPCA do exist. I've mentioned ACI, I've mentioned NPCA. There is a manufacturers trade association as well, the Fiber Reinforced Concrete Association, which is the majority of the market in terms of who is marketing and distributing fiber concrete out there. They have a section on fibers in practice, very similar to the NRMCA's FIP documents. The FRCA has an FIP section on fibers. So the industry is gathering around itself. They've agreed that working together is certainly a lot better than working apart. And we have produced documents and would love to know if there's anything that the NPCA would require from us to develop more fibers in practice, especially for specifying and using the correct fiber types that are out there. We've talked a lot today about fiber reinforced concrete and where it is and where it's going. And there's a lot of things that fiber concrete can also do. Certainly didn't want to talk much about that today, but I did want to ensure that it was well understood outside of dosage rates and engineering requirements. We did touch on a few of these, but when you have three-dimensional reinforcing, reduced plastic cracking and settlement, controlled shrinkage, better impact, less permeability, less or more improved shatter and impact resistance, increased toughness, freeze thaw, abrasion, fatigue resistance, all improved. First crack residual strength numbers, again improved. Fibers can be used as an alternative to conventional reinforcing. And so what we have today is that it's a good time to be in the business. As someone who works in this industry, we are currently enjoying rapid growth, not just in precast, but in ready mix concrete and many other applications, sustainability, ease of use, economics. This is a good time to be working with fibers. So again, if you haven't had a chance to educate yourself or would like more information on the use of fiber reinforced concrete, please reach out to your manufacturers or the Fiber Reinforced Concrete Association or ACI or your technical advisors that you have, and there are very good ones within the National Precast Concrete Association. And they can help you out with determining what types of fibers are out there, how to navigate those testing requirements, the engineering setup that are out there, and you can basically reinforce your precast application with fibers today. With that, I want to thank you. And again, I hope you are all safe and healthy wherever you may be. Look forward to seeing you on the show floor at Precast Show 2021. If there are any questions, certainly we will be available to answer those at any time. Thank you again, and on behalf of myself, I want to thank the National Precast Concrete Association for the opportunity today to present on the use of fiber reinforced concrete. Have a great day, and thank you again.